So I'm going to talk to you about a concurrency paradigm or framework known as joint calculus. And first thing I should say, thank you for inviting me. I'm a software engineer at Workday, and we use Scala, and we are hiring. Joint calculus, first of all, is not a calculus in the mathematical sense that I'm going to present. It's a programming language, and it's particularly suitable for general concurrent computations. It's unfortunately largely ignored, unknown, unused. I'm not sure. How many of you have heard ever of joint calculus? Please raise your hand. Okay, a few people. How many of you have used it? One, two. All right, I'd like to see you after the talk. I've never heard of anyone using it. Okay, so before I start talking about joint calculus as such, I'd like to talk a little bit about different notions of multitasking that we use. So there's parallelism, asynchrony, and concurrency. So I would like to very briefly discuss the differences between these things and where we stand, what joint calculus is going to give. So parallelism is basically you have a sequential computation that you're trying to speed up by executing certain parts of it on different threads or different machines. But it's basically, that's all. And the main problem in this domain is to take a sequential computation and split it into those parts that can be executed independently from each other, or parallelize. So parallel collections in Scala, or MapReduce, or Spark, those are typical examples of this kind of computation. And typical task, count words in a gazillion of files. Asynchrony means that we have a sequential computation still, but this computation has a lot of wait times. Like you're starting to download something, you don't know when it's going to be finished, you're waiting for it to finish. You'd like to start another one. Now you're waiting for two things. Now you want to start something else, update something over there. Okay, that download's finished. You're trying to manage these time delays. But basically, conceptually it's a single thread run loop that you're trying to optimize to run many things and to wait for as many things as possible at once. So that's how I see asynchrony. And to do this, people have invented things like futures promises, async await streams of different kinds, FRP, functional reactive programming, coroutines, and other things. So typical UI is built on this paradigm. So then, for example, you have an Excel spreadsheet, and the user can update any cell at any time, and all other cells need to be recomputed according to some equations. And then maybe something else can happen at any time. So that kind of thing. So that's asynchronous. Concurrency means that you have many computations running at the same time, and they are all interacting with each other in some complicated ways. So it is not conceptually equal to a sequential computation that we're just optimizing. It's actually many computations running in unknown order, and the main problem is to decide when you have to start a new one, or you should still wait and not start it because something else needs to finish first. So that kind of thing, when you start using threads or the synchronized keyword or the semaphore object, when you find yourself using those things, that's because you're trying to solve an essentially concurrent problem. So this is typical task for a concurrency is to simulate the so-called DiningPhilosophers problem, which is that 5 philosophers sit at a round table and they have food, and a philosopher can eat only if 2 forks are available. the two forks next to each philosopher. So they cannot all eat at the same time. They would like to, perhaps, but there must be some order. But this order is unknown. So one of them gets hungry at unpredictable time, another gets hungry at another unpredictable time, starts eating. So the task is to simulate this problem, to make an algorithm that will tell each philosopher what to do, not knowing how long other philosophers will choose to eat or to think after eating. Avoiding starvation and deadlock. So that is a typical problem. So I would like to summarize. So we have concurrency as the most difficult of those problems, parallelism the easiest, and asynchrony is the middle. Because the concurrency is so difficult, we try to avoid it actually. Most programmers don't like it, try to avoid it. And it's a good rule of thumb to use the least powerful framework to do what you have to do. But sometimes you do have to use all these callbacks, threads, semaphores. Shared mutable state, of course, is very difficult to reason about and very difficult to test. You have essentially unpredictable runtime behavior. You cannot test it enough. You can never test it enough. You can always expect something to happen because you didn't test it enough. So that's the difficulties like race conditions, deadlocks. Like race condition is unpredictable. It can happen. Usually you cannot prove it will not happen. It's just too difficult to reason about those programs. So in this talk, I will introduce from scratch, without any assumption about what you know, the join calculus style of concurrency. I am working on a library called join run, very small library, which implements this paradigm in Scala as an embedded domain-specific language. I'll give some examples and a very small live coding demo. And how I learned to forget deadlocks and to love concurrency. So join calculus is really a programming language, like I said. It's a declarative language for expressing concurrent programs. If you're familiar with the actors framework, how many of you are familiar with the actors framework? Oh, everybody's familiar with it. Yeah, great. I will try to skip to the slide where I compare actors with join calculus. It's like actors, if they were stateless, purely functional, automatically started, type safe, and easy to reason about. So the main metaphor that I'm going to use to explain join calculus is chemical reactions. This is based on a paper which I'm referencing up here. A paper from '96 by some French people. Very difficult to read, but unlike all other papers that are mostly also by French people on this subject, this paper contains in its introduction a very intuitively clear description of the chemical abstract machine. And that's what I would like you to think about. How I would like you to think about is imagine that we're dealing with some imaginary chemistry where we have molecules and the molecules are swimming around in some chemical solution and randomly meeting each other and producing chemical reactions. Each chemical reaction looks like some molecules meeting together, then they disappear, and the new molecule appears. And so, because it's completely imaginary, we can postulate whatever chemical laws we want. For example, that molecule A and molecule C will meet and immediately disappear into nothing. Well, that cannot happen in real chemistry. But this is imaginary chemistry. Anything can be done. And we just define whatever we want. We define any number of molecules we want and arbitrary chemical laws of reactions between these molecules. Then Imagine that we have some kind of simulator for this chemical soup. We throw some initial molecules into the soup, and the simulator starts churning them around and finding pairs that can react, producing new molecules, and so on forever. And suppose that we have this simulator, okay? Implementing that simulator is really a couple of maybe 100 lines of code. It's not so big. But that's the core of what joint calculus is about. So we will be talking about this chemical laws and chemical reactions and molecules. And that's the terminology I prefer. If you look at papers on joint calculus, you will not usually see this terminology. You'll see terminology that I find very confusing, like messages, channels. I find it very confusing, especially for the beginner. I will use the terminology of chemistry. So how do we use chemistry to actually make a programming language? I mean, it's very nice to look at some simulation of molecules, but here's what we do. Each molecule will now carry a value on it. Each molecule will be strongly typed, and it will have a value of certain type. Each reaction, not just producing a new molecule, it must produce a new value on the new molecule. And this value will be a function of the values of the input molecules in the reaction. That is our postulate. So we require this be the case. Pure function, for example, compute z, I called it, and it will compute some value z given x and y. We require that our simulator should now run all these functions whenever a reaction occurs so that new values will be computed for each reaction. So here, for example, we can imagine this reaction producing a side effect through the print statement and producing nothing, no molecules as a result. So that is an example. In principle, we can imagine that our simulator will automatically decide how many reactions can proceed concurrently. In actual chemistry, what happens is that molecules don't really know about other molecules. Once reaction started, nobody knows it started. Other reactions can start concurrently at any time. And so that's what we want the simulator to do as well. In other words, we just inject some molecules into the soup. The simulator, with some values on them, yes, now with some values, the simulator will find all the reactions that can proceed, run them, compute all the values that need to be computed according to these functions that we specify, inject the resulting molecules back into the soup, and go on. Reactions will start concurrently at any time that input molecules for the reaction are available. That is it, really. That's the entire programming language that we're going to have, except for one more feature, which I will talk later about. So this is the piece of code in the join run library, which denotes this reaction. It's completely declarative, just says, so join means that these two reactions are together in the sense that this A is the same as this A. And that is required, otherwise the molecules are not identified to be the same in different reactions. And then we say run, and you describe each reaction. So for example, A of x and B of y go to A of z. And A of x and c goes to nothing, just does something. So there's an arbitrary Scala code in here, but these constructions are a declarative description of the chemistry that we want. Here's the first example, a concurrent counter. So we have a molecule with a counter value n, and a molecule which is to decrement and to increment the counter. These two molecules have an empty value, which means unit type of the value. Each molecule is required to have a type. So these will have unit, and these will have integer type. And then we define two chemical laws. that when the counter molecule meets the decrement molecule will disappear, and the counter molecule will be re-injected back, but with the value decremented. And the same with the increment. So now you see that data stays on the molecules. We don't have any state in the language. So in the reactions, there is no state, and it's a pure function. So we just compute some pure function with some values, and that's it. So the data stays on the molecules. So it's kind of a data-driven parallelism. Now, if you imagine that we have a counter molecule, and we have 10,000 increment molecules and 20,000 decrement molecules, what will happen? Well, if we have only one counter molecule, it can only react with one other molecule at a time. So it will react first with some molecule and get decremented or incremented. While the reaction is going on, the molecules disappear. So there is no counter molecule in the soup during that time. There's absolutely no way a race condition can occur. There will decrement and increment. In time, will all be reacting with this counter molecule. At the end, the counter molecule will carry exactly the right value. There's no way that somebody can start decrementing while the other has not finished incrementing, like in the typical race condition. So how do we implement this in the library? So this is the Scala code, which I will run now, once I explain what it does. Oops, I'm sorry. Yeah. So we define the molecules using these constructions. Molecules, so the counter, decrement, increment. We specify the types. We define the reactions, which are just partial functions under this run method. And we define join, which is the two reactions together. And then we inject the molecules with values. Injecting is non-blocking. Reactions will start concurrently. So, for example, calling counter of 10, it will return immediately. It will return unit, but it will inject the molecule as a side effect concurrently. So the injection is not on the same thread usually as what you're doing here. So it's completely concurrent. Let me try to do some live coding here, although I just realized I'm holding the microphone.
How about I do this?
Oh, yeah, thank you. All right. I'm using Ammonite, which is a fantastic thing done by Li Haoyi. I just published locally my artifact, so I can import it right away. So let me define counter. I will define, let's say, decrement. I will define a reaction. I will just write a join right away, just to save time. So counter, so I'm thinking, while I'm doing this, I'm thinking about what chemistry I'm going to implement. So I have this molecule, counter, with value n. It's going to react with decrement, with unit value. It's going to produce counter, n-1. Okay, let me just do that. What happened? I forgot to say run. Scala is not good, not strong enough to infer all the types, so I need that. Okay, we're good. So I do counter 10, decrement. Well, we don't see anything, right? So there's debugging, which I put in. Now, you see, okay, I'm fine. We want to know what molecules are now in the soup and what are the values in those molecules. So in principle, this is implicit. This is not something that you see. It's not a value. The soup is not a value in principle that you can see, but there is a debugging function. So here's how it works. I do counter. Well, first of all, counter has a member which is join def, which is the join definition. And then I have a debugging tool which says print bag. So it prints the bag of molecules. And now you see, so the debug output is that there's a join definition with this reaction, counter plus decrement goes somewhere. And the soup contains molecule counter with value 8, which is what we expected to happen. Now, I suppose I could have put print statements inside reactions, and that's also a good debugging tool. But let me continue. So a very important feature that remains to be discussed is the blocking molecule feature. So far, what we have seen was all non-blocking. So these molecules react at some time, we don't know when, and the result is floating around, we don't know where it is. This is not sufficient to implement arbitrary concurrent tasks. What is missing is the blocking molecule. The blocking molecule is that, imagine that you have this molecule and you want to inject it into the soup. Now, ordinarily you just drop it and you walk away. With the blocking molecule, injection will block until this molecule starts some reaction, and then the reaction can give you a value back. Until that happens, your injection call is blocked, and you're waiting, and then you get a value back. So here's how it works in the chemistry. So imagine that F is a blocking molecule. Implicitly, it has a reply. So it has a reply functionality. So this reply functionality is represented by this reply molecule, which is implicit, which is not real. You don't define it for F. It's already implicitly defined for every blocking molecule. So this reply molecule can be injected, but when it is injected with some value, that's the value you get out of the blocking call. So this is the construction that allows you to get values and wait for some reactions to happen, and then get some responses back. So here's how you would implement in the join run library the blocking molecule. You would, first of all, define like this with two types. So this is the type that the molecule carries, and that is the type which it will return, which will reply back. Then you add a reaction. For example, counter with value x, and get n with a reply, injects reply of x, and it swallows counter, let's say. Well, we can do whatever we want. Let's do it like this, just for an example. So that will finish, that will kill our counter molecule, but it will reply with the value. So once you define the join with that reaction, you can use it like this. So this blocking molecule looks like a function that you call, it blocks while you call it, and it returns a value. So that is actually the entire extent of join calculus. Molecules, blocking, and non-blocking. There are no other constructions. I have not said the word synchronized here. I have not said the word semaphore. I have not said locking, threading, or whatever. I didn't say that. I will run through some more examples. A benchmark that I made is that I have this non-blocking counter, and I put a a lot of decrement molecules into the soup. So I initialize, oops, I'm again doing the wrong thing here. Oh. I initialize the counter with value 1,000, and I inject 1,000 D molecules, which are the decrement molecule. And that means there will be 1,000 reactions, one after another, which the runtime will have to schedule and run somehow. And I then benchmark how long that takes using a blocking molecule F, which is kind of fetch the finished value. And the finished value is the time that the reaction ran. And then I can see how many reactions my library can schedule in a second, let's say. These are very, very short reactions that don't do much. And so these reactions shouldn't take so much. So on a machine like this, I get about 100 to maybe 200,000 reactions per second. Just one word about implementation. This is backed by thread pools. It can be also backed by akka actor pools with a router. And that is actually faster. Because I'm event-driven, akka actors can schedule the closures faster than threads. But it's not a huge amount of gain. I mean, you expect to be held up in your performance by calculations and not by scheduling on closures on threads. But in principle, that's... OK, so what I'd like to say is that this is an unrestricted concurrency programming language. It can implement anything. It can implement any constructions that you want. Futures, map reduce, you can do it. I'm going to run a bit faster. This is the code for DiningPhilosophers. Okay, there are 5 philosophers and 5 forks. For each philosopher, I have 2 different molecules. I have defined T and H. So this is a thinking philosopher 1, and that is a hungry philosopher 1. And I defined the chemistry so that the thinking philosopher waits and then becomes hungry, while a hungry philosopher needs the 2 forks, so it takes a hungry philosopher molecule and the 2 fork molecules to start this reaction. Then it waits, and then it emits a thinking philosopher with 2 forks. Apart from declarations of these molecules, this is the entire code that needs to be written to simulate DiningPhilosophers. This is completely declarative. You can make lots of mistakes here because there are all these different molecules, but that's your specification. One can always make a mistake in a specification. But I write nothing else beyond writing the specification. This is fully declarative. Specifications become executable programs. Now, DiningPhilosophers is perhaps an example that is particularly suitable to be implemented in this way, and it's a very naive implementation. There is no guarantee, for example, for typical wait time before the philosopher gets to eat. There is no fairness. You could have, by chance, that some philosopher waits a very long time. You can fix all this. However, I'm just saying this is a fully declarative description of non-trivial concurrency. There are some additional features I implemented in the library. One is that I have explicit thread pools if I want. So if I know that certain reactions need to be massively parallel, I can pre-allocate thread pools for them. And and other reactions will run all on one thread, let's say, if I know that's okay. So I can do that. I can say, run this reaction on these threads from this pool, and run this reaction always on those threads from that pool. Why I wanted to implement this is that my previous experience with joint calculus was on iOS and Android, mobile applications where I implemented the prototype first. And on those platforms, you must run certain things on the so-called main thread. And if you don't do that, your application will just freeze. So you must say which reactions run on which thread sometimes. Sometimes you don't care about this, sometimes you do. So in case this becomes a problem, I have this feature. Another feature is a limited kind of fault tolerance. So what if I start a reaction and an exception is thrown? Then I can catch that and I can re-inject these molecules again to try running the reaction again. This is a very primitive kind of fault tolerance, but it just shows you that the runtime can be smart about what to do, and the programmer doesn't have to worry about it. I have some more features that I'm going to implement next. The main question here, perhaps more for the audience than for me, is what else is needed for this to be industry ready? Why is it that almost nobody is using it? So people who did use it, the 2 people here who did use it, may have the answer, but I don't have that answer. So I'll be very interested in discussing that.
My first question is, what kind of scheduling degradation do you have with large numbers of molecule types?
So
Can you repeat the question?
yeah, so the question is, what kind of scheduling degradation will I have if I have a very large number of different molecule and different types of molecules? So, so what you can do is imagine that you're scheduling all these reactions on a single thread. So the scheduling happens single-threaded, because the bag of molecules needs to be locked while you choose the inputs for each reaction. So once you have chosen them, the reaction has started, you can unlock the bag, and somebody else can start choosing molecules from the bag. But that's the synchronized part, which has to be locked, and so it cannot be multi-threaded. Unless you're very smart about what reactions can be started, and you know that it's safe to lock just one part of the bag and not other parts of the bag, but that's what I do right now. So you might have a big delay in scheduling a reaction because you have a lot of reaction to schedule and it's all done single-threaded right now. So that's maybe... Anyway, so yeah, thank you for your question. So basically, maybe these features, maybe this is the reason why nobody uses joint calculus, that nobody... So anyway, but this I don't know. Now there are some... Let me perhaps skip to some overview of other implementations, since we started discussing this issue of why it's not adopted by the industry. Now these are all the things I could have seen, I found on the web, implementations of joint calculus. Now, this a dead language, this patch to the Java compiler, dead after this time. JoCamel is alive, but how many of you use OCaml? 1? Maybe 2. Right. Compiler patch of 2003. This is Scala so old that the syntax is not the same anymore. It won't work. Okay, joins library for .NET. Microsoft research project, which you can download a binary for .NET. Scala joins. Philipp made a project. It doesn't work very well. It has many limitations. Jiansen made an improvement of that. Still has many limitations, but that's what I'm building up on. Join ads, again, Microsoft research stuff. Now, my projects, my prototypes for Android and iOS, I don't think a lot of people use that. This is an Objective-C. And this is plain Java, which is Android specific, so it won't run without Android libraries. So what of this is industry ready? Which one of these? This is why I'm trying to push this. I'm trying to develop a better prototype with more features. Another problem I should mention is lack of documentation about joint calculus. If you read tutorials that are not written by myself, you will not understand them, I guarantee. You will be completely confused by terminology, by lack of clear examples of what you want to do. There are other approaches to concurrency, of course, act as actors. Let me do a comparison briefly here. So actor is like a reaction, and an injected molecule is like a message sent to an actor. Except that actors need to be created and managed explicitly in your code. Actors will process one message at a time, and they will typically hold mutable state. Reactions will start automatically whenever the required inputs are available. You don't explicitly start them. You don't allocate them. You just define that they should start. This is what you want to be happening. Many reactions can start at once, yes. Reactions can require many molecules at once, rather than just one. And this seems to be a difficult thing to understand, maybe, if you think about actors. But when you think about reactions, that's natural. You need different pieces of data, and once you have them, you can do something. In my view, this is kind of a data-driven concurrency. It is not thread-driven concurrency. It is not process-driven concurrency. It's data-driven. You have data, you can start working with it. If you don't have data, you just wait. What am I supposed to do? I don't have the data. I need to wait for it. But actors are kind of complicated. I mean, this is the documentation for the actor class, and these are the things you need to understand. Okay, all these things, you need to understand them. And that was item 1. And there are 14 further items in the documentation. So that's kind of complicated. If you compare this with, this is what you need to know about joint calculus, that's all. These are the concepts, these are the syntax, that's it. You're good to go, you just use it. Let me, before I conclude, I just have maybe, I have very little time, but let me show you a merge sort example. Okay? So this example illustrates an interesting feature that reactions are defined in local scope. They're not somehow globally defined. They're defined in local scope. They're values. Molecule, all these reactions, they're just values. They're defined in local scope. So what you can do is you can define a recursive molecule that defines new reactions in its local scope. And then this is how merge sort is implemented. Merge sort defines its own sorting reactions in its scope, injects the inputs for these reactions, gets the result, merges them, and returns. So this is the skeleton code for merge sort. You define this new reaction, and then you inject itself with these molecules, which it will inject and so on until you get, well, this is just a skeleton. The full code is here. Not much more complicated. It actually works. I'm out of time, but let me just give you the conclusions. Joint calculus is the best ever declarative, purely functional concurrency model, which is more purely functional than anything else you've ever seen. And actors is just complicated, and you don't want to use that ever. However, even though this is all true, joint calculus is never used. So partially because the existing literature is not suitable as an introduction, and partially because the implementations are lacking. I'm trying to fix both of these at once. So keep this space under your supervision, learn about joint calculus, and use it. Thank you.
Okay. We're actually going to get set up for the next speaker, so if we have questions, I would recommend you each come up here and we